Hello student, in this video I am going to discuss about uh, geometric transformation in three-dimensional space. We have studied the two-dimensional transformation by including a homogeneous coordinate system. Here also, same like 2D transformation, or you can say two-dimensional transformation, we can extend that same idea by including the consideration for the z coordinates. Translation and scaling are similar to the two-dimensional transformation, including the three Cartesian coordinates. Rotation method is less straightforward, means they are a bit complexity. So in case of three-dimensional space, we represent the matrix as a four-element column vector to make it a homogeneous coordinates, and that is why this three-dimensional geometric transformation is described by, or you can say as, 4 by 4 matrix. Suppose you want to do a transformation in three-dimensional space. Suppose you have the point P, X, Y, Z in three-dimensional space, and you need to translate to a new location with the translation distance t, tx, ty, tz. Then matrix formation, like here you can see x dash will be the new point value, x plus tx, this is the old point value with the translation factor in the x direction. This is y dash, y plus ty, this is z dash equal to z plus tz. Here you can see x dash, y dash, z dash, and 1, that is why this is homogeneous coordinate system, and we have created like 100tx, that is a translation factor in the x direction, this is y direction, this is z direction, and we have multiplied with x, y, z, 1. So this is the old values of the point, this is the p value, so p dash equal to t dot p, and the multiplication value will be x, y, z, y dash, z dash 1, which is the new point after applying the translation factor. Same type we can apply. Here you can see three-dimensional scaling. It is related to coordinate origin. If we want to do that scaling with respect to origin, just include the parameter for z coordinate scaling in the transformational matrix as like the 2D matrices. Here you can see x dash, y dash, z dash 1, and just you can include the or you can say you can include the scaling factors here in diagonal way, so that it can be applied with the xyz value of the p to get the new value p dash after applying the scaling factor s in all direction of the three-dimensional space. Again, we can do that same thing with respect to a fixed point also. So what will happen if we apply with respect to fixed point xf, yf, zf, perform a translate scaling translate composite transformation. So if we want to translate an object, if we want to do a scaling of an object with respect to a fixed point, then first we need to translate the object from the so that we can do that scaling operation with respect to origin. Then we scale the object with respect to origin, then again we translate back the whole object, whatever factor we have translated in the first phase, that has to be again translated back. Here you can see t, xf, yf, zf, xx, xy, sz, t minus xf, yf, zf. So here you can see sx, sy, sz as like the original scaling factor, but that translation happens here. First, that is the 1 minus sx, means whatever distance has been reduced or increased due to these two translation factor after applying the scaling factor. So that is a 1 minus Sx into Xf. Due to the scaling, whatever translation occurs, that part need to be multiplied with the Xf, with the scaling factor, with the translation factor Xf. Okay, there is a Xf, here you can see Xf, here you can see minus Xf, and both are multiplied with Sx. So that is a 1 minus Sx and common that part Xf. So in that way, if you solve this thing, the multiplication part, you will obviously find this one. So that is the factor will be translated when we apply the scaling with respect to fixed point. Okay, that is the factor that will be applied if we apply that scaling with respect to fixed point, and that much amount of translation will occur to that object, and that can be derived using following this composite transformation multiplication. The composite transformation is combined with like translation first, so that we can translate the object, or we can scale the object with respect to origin, then again translate back, with the same amount of you have translated previously. So we have already discussed that that scaling and translation is same like 2D dimension, 2D space, but rotation in case of 3-dimensional space is a bit complex. Let's see how it follows. Suppose there is 3 dimension. Here you can see, if you are looking from z direction to the negative end of the z direction, if you are looking from the x direction, from the negative end of the x direction to the negative end of the x direction, or you might look the object from the y direction to the negative end of the y direction. Assume looking in the negative direction along the axis. The axis might be any one of the 3 axes, and then positive angle rotation produces counterclockwise rotation. If you rotate the object in a positive angle, then the object will rotate in a counterclockwise rotation about the coordinate axis. So that is counterclockwise rotation about the axis, through which axis you want to rotate. Through which axis you want to rotate, through that axis that object will rotate. And if it is if the angle is positive, rotation angle is positive, then it will go through counterclockwise, okay, about that axis in whatever direction you are looking at. Okay, it might be x, it might be y, it might be z. So let's see how the equation behaves. Here you can see, if you choose the z axis rotation, 3-dimensional coordinate axis rotation, like here you can see, you can choose z axis rotation, then your equation will become like this. Because if you do this z axis rotation, then values of the coordinate of z will be same, but the values of x dash and y dash will be changed. That is, x dash and y dash will be multiplied with the factors, that is rotation factor, which can be calculated using the angle rotated, and if it is positive, it will be like this. So that is Rz. So transformation equation for rotation about the other two coordinate axes can be obtained by a cyclic permutation. So if you want to do the 3-dimensional coordinate axis rotation, then you need to apply, if there is any rotation with respect to z axis, then first z, then x. If you are in x, then apply y. So transformation equation, that is very important point. This is very important point. Transformation equation for rotation about the other two coordinate axes can be obtained by a cyclic permutation. So if you do first x rotation, then you have to do the y then and then z. Not like x first, z second and y last, or like z first, x second, y z first, x third, y first, like that. So here you can see z first, then we might go to x, then we should go to y. So after applying the z rotation, if we apply the z rotation, then we will apply this. If we after that we will apply x, then x will become like this x, then the angle will be applied. Then again, if we apply y in the y direction, then it will become this. So here you can see applying all the three axis rotation to find the actual rotation of the object. Okay, so general three-dimensional rotation follows this process. If we need to translate objects so that rotation axis coincides with the parallel or coordinate axis, to perform the specified rotation about that axis, translate back object to the original position. So this is a general procedure, but if you want to do the thing with respect to origin, then no need to go with that. But as a general, suppose you want to rotate an object with respect to any point, then you need to translate the object first so that the rotation axis coincide with the parallel coordinate axis. So here you can see in previously we have shown one diagram here. If you do in that parallel with in this parallel direction of the z-axis, then first suppose at any position that the object might have, but you have to make it parallel to that z-axis if you want to do the rotation first with respect to z-axis, because the object you are going to rotate, it might be in any direction, but if you have to apply in a cyclic permutation, like first z rotation, then x rotation, then y rotation. So in that way you will follow. So that is why in whatever direction you are going to apply, in that direction you have to make it parallel. Here you can see translate objects so that rotation axis coincide with the parallel coordinate axis, perform the specified rotation about that axis, and again translate that object back to the original position. So this is a composite transformation. So but point is that you have to go with all these three axis rotation. So here you can see this is the last part of this three-dimensional space transformation. Here you can see if we do the inverse of a rotation matrix, r inverse theta, that is equal to r minus theta. Inverse means in negative direction, that is cos minus theta equal to cos theta, sin minus theta equal to sin theta. So here you can see r inverse theta will be equal to this, which is the transpose of r, because you can see the value of r is actually in that scenario. You can see if you apply the x-axis, here you can see in the x-axis like this. Here you can see this is the equation. So here this is the equation of the general rotation. So it will become like this, so in the z direction. So here one thing you can prove it like that, r minus 1 equal to r of minus theta. So here you can r in minus 1 means r inverse equal to r transpose. So in that scenario we can say that this thing makes it like that the matrix is orthogonal form. The matrix is orthogonal. So that is all about. There are lots of things also need to know regarding the geometric transformation in three-dimensional space. You will find lots of other knowledge or important aspects in the books also. Please try to follow that. I have just mentioned few interesting or required points through this video, and if you have some doubt or any anything need to ask, please let me know. I will try to resolve that thing over Google Meet. Thank you.